Hi guys, this video is about the Nobel Prize in Chemistry for the year 2023, and this Nobel Prize was jointly shared by Moungi Bawendi, Louis E. Brus and Aleksey Yekimov for the discovery and development of quantum dots. So in this video we will see the popular science background, that what are the quantum dots, how they were discovered, how they were tuned, or how they were developed and converted into some applications. So this video is all about quantum dots, and if you like this video, please like, share and subscribe this channel. So first of all, we will see that what are the quantum dots. So in this picture, it has been illustrated here. This is the quantum dot, and it is actually a crystal that often consists of just a few thousand atoms. And in terms of size, it has the same relationship to a football as a football has the size of the earth. In the nano world, things really do behave differently. Once the size of matter starts to be measured in billions of a millimeter, strange phenomena starts to occur, which is also known as quantum effect. The 2023 Nobel laureates in chemistry have been pioneers in the exploration of this nano world. In the early 1980s, Louis E. Brus and Aleksey Yekimov were succeeded in creating independently of each other quantum dots, which are nanoparticles so tiny that quantum effects determine their characteristics. While in 1993, Moungi Bawendi revolutionized the method for manufacturing quantum dots, making their quality extremely high, a vital prerequisite for their use in today's technology. Thanks to the work of these laureates, humanity is now able to utilize some of the peculiar properties of this nano world. Quantum dots are now found in commercial products and used across many scientific disciplines from physics and chemistry to medicine. But we are getting ahead of ourselves. So let's uncover the background to the Nobel Prize in Chemistry in 2023. Quantum dots have given us opportunities for creating colored light. So if you see here, uh, these dots are representing the quantum dots, and these are actually different in size. So it means bigger the size, more reddish the quantum dots will be, smaller its size, more bluish it will be. So in this way, we can get a rainbow of colors from these quantum dots, which are varying just because of their size. When Aleksey Yekimov and Louis Prus produced the first quantum dots, scientists already knew that they could in theory have unusual characteristics. In 1937, the famous physicist Herbert Follisch had already predicted that nanoparticles would not behave like other particles. He explored the theoretical consequences of the famous Schrödinger equation, which shows that when particles become extremely small, there is less space for the material's electrons. In turn, the electrons, which are both waves and particles, are squeezed together. So Follisch realized that this would result in drastic changes to the material's properties. So researchers were fascinated by this insight, and using mathematical tools, they succeeded in predicting numerous size-dependent quantum effects. They also worked to try to demonstrate them in reality, but this was easier said than done because they needed to sculpt a structure that was about a million times smaller than a pinhead. That looked impossible at that time. Before jumping into how different quantum dots produce different colors, let's have a background about the colored glass. The oldest archaeological finds of colored glass are often several thousand years ago. Glassmakers have tested their own way to an understanding of how glass can be produced in all the colors of the rainbow. They added substances such as silver, gold, cadmium, and then played with different temperatures to produce beautiful shades of glass. In the 19th and 20th century, when physicists started to investigate the optical properties of light, the glassmakers' knowledge was put to use. Physicists could use the colored glass to filter out selected wavelengths of light. To optimize their experiments, they started to produce glass themselves, which led to important insights. One thing they learned was that a single substance could result in completely different colored glass. For example, a mixture of cadmium selenide and cadmium sulfide could make glass turn either yellow or red, which one it became depend on how much the molten glass was heated and how it was cooled. Eventually, they were able to show that colors came from particles forming inside the glass and that the color depend on the particle size. This was more or less the state of knowledge at the end of 1970s when one of this year's laureates, Alexey Yekimov, a recent doctoral graduate, started working at SI Vavilov State Optical Institute in what was then the Soviet Union. The fact that a single substance could result in a different colored glass interested Alexey Yekimov because it is actually illogical. Like if you paint a picture in cadmium red, it will always be a cadmium red unless you mix it with other pigments. So how could a single substance give glass of different colors? So in order to find the answer of this question that how a single substance can give a different color, Yakimov started different experiments on colored glasses. So after some initial experiments, he decided to systematically produce glass that was tinted with copper chloride. He then heated the molten glass to a range of temperature between 500 and 700, varying the heating time from 1 hour to 96 hours. Once the glass had cooled and hardened, he X-rayed it and the scattered rays showed that tiny crystals of copper chloride had formed inside the glass and the manufacture process affected the size of these particles. In some of the glass samples, they were only about 2 nanometers. In others, they were up to 30 nanometers. So, interestingly, it turns out that the glass light absorption was affected by the size of particles. The biggest particles absorb the light in the same way that copper chloride normally does, but the smaller particles the blur the light they absorb. So, as a physicist, Yakimov was well acquainted with the laws of quantum mechanics and quickly realized that he had observed a size dependent quantum effect. And in this figure, this effect has been explained here. So, if you see there that when particles are just a few nanometers in diameter, the space available to the electrons shrink. So this affects the particle's optical properties. So if we see here, this is the particle of larger size, then the size is decreasing. So this is that wave which was representing here by some electron. So here if you see here, this wave has a greater diameter because it has more space available, whereas as the size is reduced, this wave has been squeezed continuously, and as a result of which when particles are just a few nanometers in diameter, the space available shrinks so much that optical properties are varying with one another. So if we see here that there are large nanoparticles, more space for the electron wave, smaller nanoparticles, less space for the electron wave. So when quantum dots absorb the light and then emit it, then the color of the emitted wavelength is different depending upon the size. Like if we see here that particle is of larger size, that it will emit a red wavelength. If the size is small, then the same amount of energy released, then the light it will release will be of shorter wavelength or more bluish in tone. So in this way, by varying the size of the particles, we can have a light of different color which is emitted from these particles. In 1981, Yakimov published his discovery in a Soviet scientific journal, but this was difficult for researchers on the other side of the Iron Curtain to access. Therefore, this year's Nobel laureate Louis Brus was unaware of Alexey Yekimov's discovery when in 1983 he was the first researcher in the world to discover size-dependent quantum effect in particles floating freely in a solution. Louis Brus was working at Bell Laboratories in the US when the long-term aim of making chemical reactions happens using solar energy. To achieve this, he was using particles of cadmium sulfide which can capture light and utilize its energy to drive reactions. The particles were in a solution and Brus made them very small because this gave him a larger area on which the chemical reactions could take place. The more a material is chopped off, the greater the surface area it will expose to its surroundings. During his work with tiny particles, Brus noted something strange. Their optical properties changed after he had left them on a lab bench for a while. He guessed that this could be because the particles had grown. So, to confirm his suspicion, he produced cadmium sulfide particles that were just about 4.5 nanometers in diameter. Brus then compared the optical properties of these newly made particles with those of larger particles which have diameter of about 12.5 nanometer. The larger particles absorb light at the same wavelength as cadmium sulfide generally does, but the smaller particles had an absorption that shifted towards blue. So just like Yakimov, Brus understand that he had observed a size dependent quantum effect. He published his discovery in 1983 and then started investigating particles made from a range of other substances. The pattern was the same: the smaller the particles, the bluer the light they absorb. So, why does it matter if a substance absorbance is slightly more towards blue? Why this is so amazing? Well, the optical changes revealed that substance characteristics had completely changed. A substance's optical properties are governed by its electrons. The same electrons also govern the substance's other properties, such as its ability to catalyze chemical reactions or conduct electricity. So, when researchers detected the changed absorption they understood that in principle they were looking at an entirely new material. The magnitude of this discovery can be understood from the fact that the periodic table suddenly gained a third dimension. For example, an element's properties are not only affected by the number of electron shells and how many electrons are there in the outer shell, but at the nano level, size also matters. A chemist who wanted to develop a new material thus had another factor to play with. Of course, this tickled researchers' imaginations. However, there was a problem. The method Brust had used to fabricate nanoparticles generally resulted in unpredictable quality. So, quantum dots are tiny crystals, and that ones that could be produced at a time often contain defects. There were also of varying sizes. So, it was possible to control how the crystals were formed so that particles had a given average size. But if researchers wanted all the particles in a solution to be about the same size, they had to sort them after they were made. This was a difficult process that hindered the further development. So, this was a problem that this year's third Nobel Prize laureate in chemistry decided to solve. Moungi Bawendi started his postdoctoral training in Louis Brus laboratory in 1988, where intensive work was underway to improve the methods used to produce quantum dots. Using a range of solvents, temperatures, and techniques, they experimented with a variety of substances to try and form well organized nanocrystals. And the crystals were getting better but were still not good enough. Bawendi did not give up. When he started working as a research leader at Massachusetts Institute of Technology (MIT), he continued his efforts to produce higher quality nanoparticles. The major breakthrough came in 1993 when the research group injected the substances that would form nanocrystals into a heated and carefully chosen solvent. They injected as much of the substance as was necessary to precisely saturate the solution, which led to tiny crystal embryos beginning to form simultaneously. Then, by dynamically varying the temperature of the solution, Moungi Bawendi and his research group succeeded in growing nanocrystals of a specific size. During this phase, the solvent helped give the crystals a smooth and even surface. The nanocrystals that Bawendi produced were almost perfect, giving rise to a distinct quantum effects. Because the production method was easy to use, it was revolutionary. More and more chemists started working with nanotechnology and began to investigate the unique properties of quantum dots. The luminous properties of quantum dots are utilized in computer and television screens based on QLED technology, where the Q stands for quantum dots. In these screens, blue light is generated using the energy efficient diodes that were recognized with the Nobel Prize in Physics in 2014. So, Quantum dots are used to change the color of some of the blue light, transferring it into red or green. This makes it possible to produce the three primary colors of light needed in a television screen. Similarly, quantum dots are used in some LED lamps to adjust the code light of the diodes. The light can then become as energizing as daylight or as calming as the warm glow from the dimmed bulb. The light from quantum dots can also be used in biochemistry and medicine. Biochemists attach quantum dots to biomolecules to map cells and organs. Doctors have begun investigating the potential use of quantum dots to track tumor tissues in the body. Similarly, chemists instead use the catalytic properties of quantum dots to drive chemical reactions. So, quantum dots are thus bringing the greatest benefit to humankind, and we have just begun to explore their potential. Researchers believe that in the future, quantum dots can contribute to flexible electronics, minuscule sensors, slimmer solar cells, and perhaps encrypted quantum communication. One thing is certain that there is lot left to learn about amazing quantum phenomena. So this was all about the discovery of quantum dots and their various applications, and the Nobel Prize in 2023 chemistry goes to quantum dots and their discovery.